Okay, so let's welcome to new lecture, lecture 15. So in this lecture, we'll again continue talking about structure of metals with a focus on packing of atoms in these structures, coordinations, and interstices. Okay, so let me just recap the last lecture. So in the last lecture, we started about structure of metals. Okay. So here we basically talked about how atoms pack closely in metallic structures. They pack themselves in face-centered cubic or cubic close-packed structure and hexagonal close-packed structure by the virtue of arrangement of layers in AB. So each layer is hexagonal sort of layer in nature. So if you have an array of atoms like this, then each layer underneath is like this. So this is how, and you can keep extending it in two directions. So this is how your first layer is going to be. Now if this is A layer, when you put that B layer on top, the B layer can go on this type of interstices or this kind of interstices. So if it, let us say this interstices will give rise to B layer and this interstices will give rise to C layer. So if you follow the stacking sequence of ABC, ABC, then what you come up with is a cubic close-packed structure. This can be described by a FCC lattice with a motif at 0, 0, 0. Okay. So this is ABC, ABC packing. If you go think about, if you pack in a AB, AB stacking kind of sequence, where so you put the next layer at B, then the next layer again comes back on A. You don't have to necessarily go to C, which is again alteration of ABC, ABC type of packing, but both are close packed structure. This is called as hexagonal close packed structure. However, in this case the lattice is primitive, it is not primitive hexagonal, okay, with a motif at 0, 0, 0 and 1/3, 2/3 and half. So it is a 2 atom motif here. In this case it is a single atom motif by which you can define the lattice. Single atom motif with FCC lattice will mean that you have one atom at 0, 0, 0, another at half of 0, another at half 0 half, and another at 0 half half. Okay, that will automatically, the moment you describe the lattice type as F. So that is the condition. Okay, so this is where we were in the last class. So this class we will again look at some other structures. So not only your metals can, in metals atoms arrange themselves in ABC, ABC type of packing, there are other structures as well. For example, if you have atomic arrangement like this, right, and this is your next layer, and so on and so forth. So you can put the next layer, if I use a different color here like this. Now this is not the close, and so this is your sorry, so this will be B layer and the first layer will be A layer, and then again on top you can put a layer. So this is, but however in this case you can see that the A layer is not closely packed. Okay, the number of atoms which surround each A atom in this case is different. So if you look at the close number of nearest neighbors, in A layer is, each atom is surrounded by, so if you have this kind of packing, and if you talk about this particular, let us say A guy, so you have one this as a nearest neighbor, another one this as a nearest neighbor, another one this as a nearest neighbor, another one this as a nearest neighbor. So number of nearest neighbors are In the close packed case, what was the situation? It was 6. So this means this is less close packed. Okay. So you can find out also the atomic density in this layer by just calculating the number of atoms per unit area. And this sort of structure, if you have this kind of stacking, then what it gives rise to a structure which is something like that. Try to remake it. Okay, so for the sake of illustration, the atoms are not touching here, and one atom will be at the center. Okay, so these will be at 0, 0, 0 position, and this will be at half position. So this kind of lattice is called as body centered cubic. So here you can see that this structure is less closely packed as compared to hexagonal close packed or face centered cubic structure. We will see the atomic packing factor in a little while. So this is another possibility that can occur in case of, so basically if you just want to look at it from the perspective of, so if I just put another layer on top, the another layer on top would be something like that. So the unit cell would be this unit cell, the one in the yellow here. Okay, so that would be the unit cell. So it has 2 atoms at the center. It has 2 atoms in the unit cell. Sorry. So one at the corner at 0, 0, 0. So 2 atoms per unit cell. So this lattice type is BCC, which is I. So when you define the lattice type as I, then the motif becomes, motif is 0, 0, 0, single atom motif at 0, 0, 0. Okay. When you define a lattice type as non-primitive, you don't need to define the coordinates of all the atoms in motif. You just need to define only one atom which is at 0, 0, 0. It will, so I symbol will ensure that the number of atoms in the unit cell, one is at 0, 0, 0, another is at half, and they are identical. They are identical lattice points. So it has 2 lattice points per unit cell. They are identical. So this is 2 lattice points. So I ensures that you have 2 lattice points. But to define the motif, you can just use single atom motif at 0, 0, 0. Similarly, in case of FCC, single atom motif will be at 0, 0, 0, but it ensures that you have 4 identical lattice points, one at 0, 0, 0, another at half 0, 0, another at half 0, another at 0, half. Okay. So this is another lattice type in metals which is quite common, and the third one, which is not so common, could be in this kind of. So you have this arrangement, sorry, the fourth one. So you have atoms in this fashion. This is the layer 1. Second layer goes directly on top of it. So if you look at this structure, it will look like alright. So this is one atom, this is another atom. They are kept apart for the sake of illustration, but they do touch each other. This is simple cubic. So here each atom has how many nearest neighbors? 6 nearest neighbors, but within the plane it has only 4 nearest neighbors. So likewise, in case of BCC, number of nearest neighbors were 8 in 3D, right. So this atom is surrounded by 8 of the atoms. Similarly, this atom is surrounded by 8 atoms. So one in the center is same as, so I have although dashed it, but they are both same atoms. Okay. So this is called as a simple cubic lattice. The lattice type is defined as P, which is primitive, and motif is at 0 0 0. Okay. So these are the 4 type of lattices we typically find. The examples of, for example, HCP based metals are beryllium, cadmium, magnesium, one form of titanium. These are all metals. Some alloys, for example, brasses, titanium alloys, they are also hexagonal in nature. And then you have FCC based metals. FCC based metals like platinum, gold, copper, nickel, all of them are FCC based metals. And then BCC based BCC structured metals are things like iron, tungsten, molybdenum. These are all BCC based material. And then simple cubic is polonium, PO. This is perhaps the only metal in the periodic table which is simple cubic structured. So in this case, so in case of FCC structured materials, we define a close packed plane, the plane which is absolutely close packed. Okay. So this plane is 111 plane, and in this plane lies a close packed direction which is of 110 type. This can be illustrated by this bracket. Okay. So of course, if you take this type of 111 plane, then the directions which will lie in this will be bar 110, 10 bar 1 and 01 bar 1. The dot product of the direction which lies in a plane should be equal to 0. Okay. So there are these close packed planes and directions in case of FCC. In case of HCP, the close packed plane is 001 or 0001, which is also called as basal plane. And the close packed directions you have only, so if you look at hexagonal system, this is right, this is the plane. The directions, close packed directions are, this is a close packed direction, this is a close packed direction, and this is a close packed direction. So if this is A1, this is A2 and this is A3, you can write in 2 coordinate system, 3 coordinate system. So this is 100, this is 010 direction. So you can have 100 or 010, but since this is also a direction which otherwise will turn out to as a 110 direction, so you need to modify this. So what will that direction be? So you will have 10 bar 10 type of directions. So this will ensure 10 bar 10, 0 1 bar 0 and 1 bar 1 0 0. So these 3 directions will lie within this plane. So there are only 3 sets, 1 plane and 3 directions. In case of FCC, there are multiple choices. 111 planes are, there are 4 types of 111 planes. Family has 8, but equivalent, if you don't consider equivalent planes, then there are these 4, and then you have 3 types of directions in each of them. So total possibilities are 12. In this case, so this 4 into 3 will be 12. Okay. So we will see this in the mechanical behavior. This is called a slip system. In case of mechanical properties, we consider this as a slip system because on this plane the mechanical deformation happens in FCC structured materials. So there are 12 slip systems in FCC. In case of HCP, there are only 3 slip systems, 1 multiplied by 3. Okay. Now, in case of BCC, there is no close packed plane. Okay. The plane which has the highest density of atoms, which is like this. Okay. So there is no close packed plane, but there is a close packed direction. All right. Sorry, not this, let me just draw the BCC cell again. Just so this is the BCC cell. So close packed plane means the plane having highest atomic density. So there is no, since there is no hexagonal packing of atoms in BCC structured, there is no close packed plane, but there is a close packed direction. In this direction the atoms touch each other. Okay. So BCC has a close packed direction which is 1 1 1 1 1 1 1 1 1, and there are multiple types of this 1 1 1. So basically, since it is a cubic structure, you can write this as 1 1 1. So 1 1 1 types of directions are close packed directions. There is no close packed plane because there is no plane with that hexagonal arrangement of atoms which is the highest possible density of atoms in a plane. However, in this case, in metals, in single atom case, however, what may happen is this direction may lie within a plane. So if you just take the so this direction lies in a few types of plane. So 1 1 1, there are few possibilities. 1 1 1 direction may lie in a plane which is the 1 1 0 type of plane. It may lie in a plane which is 1 1 2 type of a plane. It may lie in a plane which is 1 2 3 type of plane. Okay. So this is a possibility that may exist. Sorry, not this kind of. This is a plane. So for plane we use this symbol, and this is. So if you work out the combinations will be total of 48. Okay. So this is again something which is used in mechanical behavior of materials. In case of simple cubic, the close packed direction is nothing but 1 0 0 type of direction. This is the close packed directions along which the atoms touch each other, and by the virtue of that it lies in it may lie in several types of planes. All right. This is basically you can find out the type of planes in which it can lie. But it's not a close packed structure, it's only one metal, so we just generally don't consider the slip system in this case. So now once we have seen the 4 types of these lattices with their close packed planes and directions, we will now move on to what is called as coordination number. Okay. Coordination number is basically the number of nearest neighbors, So for HCP or FCC case, as we have seen in the close packed structure, so you have arrangement like this, right? Next atom goes, let us say this is the atom which is the next layer atom, okay, and then again the next layer, if it is the next layer will go, either it will go on top of A or it will go on top of B. So either it will be ABC or it will be, no matter what the case is, this atom will be surrounded by, so within the plane how many neighbors will it have? 1. So within the, let me just, sorry. So this is, let us say, one layer. 3, 4, 5. Within the layer it has 6 neighbors within the layer, 6. And if it has a layer up or down, then it can have one atom here, and one atom somewhere here. How many it will have? It will have out of the layer 3 on top and 3 on bottom. So how many nearest neighbors it will have? 12. Total of 12 nearest neighbors it will have. I will just give you a short animation of that. Let me see if I have a slide. So, if you just look at this animation, there is the first layer, there is the second layer. So, it has 3 below, 6 within plane. You can see that 3 below are the ones which are 1, 2, 3, all right. 6 within the plane, 4, 5, 6, 7, 8, 9, then 3 on top, 10, 11, 12, and you can just fill it now. So, each atom has 12 nearest neighbors in FCC or HCP structure. So, this will have 12 nearest neighbors. So, coordination number in case of this is 12. In case of BCC, the coordination number is 8, which was obvious. In case of simple cubic, the coordination number was 6. Okay. So, you can see that number of nearest neighbors is largest in case of a close packed structure. As a result, there is a quantity called as atomic packing factor. Which is highest in case of FCC. What is atomic packing factor? Which is APF, is basically volume of all the atoms in the unit cell divided by volume of the unit cell. So, let's see in case of FCC. Okay. In case of FCC, you have a situation like this. So, I will not draw the atoms touching with each other, but they do touch each other, okay, for the sake of illustration. So, this is the scenario you have, all right. Now, so in case of FCC, let us say the unit cell parameter is equal to A. So, unit cell parameter is A. Radius of an atom is R. So, I can see that the atoms touch along the faces. Okay, I know that the atoms touch along the faces. If they touch along the faces, then what is the relation between R and A? So, face diagonal length is equal to A root 2. This is equal to, this is 2R, this is 1R, this is 1R. This becomes equal to 4R. So, A is equal to 2 root 2 R. So, volume of unit cell V unit cell is equal to A cube, which is equal to 2 root 2 R cube, all right. Now, volume of, so and how number of atoms are 4, volume of one atom is 4 by 3 pi r cube. So, APF can be worked out as 4 into 4 by 3 pi r cube divided by 2 root 2 r cube. So, this will be 16 pi by 3 r cube. This will be equal to 8 into 2 16 root 2 r cube, and this will work out to be nearly 0.74, I think. Okay. So, this is how you determine the atomic packing factor. So, as an exercise, you can determine the atomic packing factor of BCC, simple cubic and HCP structures. HCP, you can see it will come out same as FCC because both are close packed structures. Okay, so FCC, it will be same as FCC, but it is determined in a different manner. It's not the same manner as FCC. Simple cubic and BCC will be lower than CCP, but you need to work out what these numbers will be. You can see by intuition that FCC HCP is the highest, BCC is the second highest, and HCP is the simple cubic is the lowest. So this will be the atomic packing factor of these materials. Now last thing I wanted to cover in this, perhaps we won't be able to go to interstices, is in case of HCP crystal, HCP lattices, there is something called as C by A ratio. Okay. Now in case of a hexagonal close packed, we know that there is a okay, and the next set of atoms goes, one goes here, another goes here, and another goes here. Okay. This is the B layer, and the another next layer will again be, it will be this layer. I am slightly displacing it so that it is clearer to you. It will be this layer, it will be this layer, this layer, and it will be this layer. Okay. So basically, what is the A parameter in this case? If you just take the now, if you just draw the unit cell, the unit cell is something like that. You have one atom here, one atom here, one atom here, one atom here, another here, another here, another here, another here, and one in between. Between these three atoms and these three atoms, right between these three atoms you have one atom. So this is the atom. So this is one triangle. If you just draw the top view would be like this. This is one atom, this is another atom, these are all become little and this will be sitting here. Okay. So what we need to determine is, if this is A, this is C, when atoms are touching each other, what is the ideal C by A ratio in a FCC structure? So basically we need to find out. So if you look at the structure now, ideal C by A ratio, if this atom, if you connect this atom with the atoms below, if you connect this with that, this with that, this with that, what does it make? It makes a tetrahedron, right? It makes a regular tetrahedron. So basically what you have here is, you have something like that. A regular tetrahedron like this, which has a height, let us say this is the, so if I just draw, so this let us say is the center of this tetrahedron. So let us say this point is the distance between these two is h, which is equal to C by 2, all right. So we need to determine these points. This is V, let us say, this is F, and the center and the center of this tetrahedra is somewhere which is called as C. Okay. So by geometry, now you need to work out that. So you know that these distances are, what is this distance? This is A, which is equal to 2r, because you have an atom sitting here, right? You have an atom here, you have an atom here, you have an atom here, and you have an atom here. They are all touching each other, right? So, all the sides are 2R, this is 2R, this is 2R, this is 2R, and even this one is 2R. All of them are 2R, and 2R is equal to A. Okay. We need to find out what H is, which is C by 2. So, by geometry you can work out this distance CV is equal to root of 6 by 4 into A, and CF will be equal to root of 6 divided by 12 into A, and we know that H is equal to CF plus CV. So, this will be root of 2 by 3 into A, and ideal C by A ratio in this case will be equal to 2H divided by A, which is equal to 2 into root 2 divided by 3, and this will be equal to 1.632. Okay. So, I will leave it to you as a homework to work out this analytically. What will CV be? It's simple geometry, nothing else. Okay. These are all equilateral triangles with the angles between the apexes being 60 degrees. So, this is a 60 degree angle, this is 60 degree, this is 60 degree, this is 60 degree, this is 60 degree. So, it is very simple, straightforward geometry, and try to work it out, and there are plenty of books from which you can take the help. So, CV will, you need to first determine what is CV, and then you need to determine what is CF, and once you determine these two using geometry, you can determine what is the height of the tetrahedron. All right. So, this is where we will end this lecture. In the next lecture, we will talk about interstices in these structures, and structure of some common metals and alloys. Okay.